All right. Thanks everybody for coming to another great edition of Adam's meetings for the ASU Hacking Club. Today we're going to be doing more assembly stuff, so hope you guys came ready with your VM. We got some classic announcements for the club as usual. This weekend we have another CTF. It's going to be pretty fun. It's Tasteless CTF. It starts on Saturday. It starts really early on Saturday, 6 a.m. So it's likely that most of us are going to start playing around 10 a.m. If you guys are on campus, feel free to come and play with us at Brickyard. We're going to be playing on the 4th floor at Brickyard Engineering in the CEFCOM lab, so you can just stay posted in the Tasteless CTF channel, and we'll keep you updated. So we'll probably come there around 10 a.m. And aside from that, we don't really have too many other announcements. Nobody has ascended to being a member this week yet of the club, so get back to the membership challenge and get yourself some membership. And that's about it. All right, Adam.
Well, I need you to keep vamping.
All right, more vamps. I'll keep stalling. Yeah, why isn't anybody doing the membership challenge, man? What the heck? Well, I guess we have a few people, and we haven't taught overflows yet or anything. So, hint, hint. It's a major part of the challenge. So.
Whoa, you're giving it all away.
I know. I just destroyed the challenge. There's a lot of parts though. There's like 3 parts. So.
Okay.
Fun, good times. Also, if you didn't take a look at the assembly modules, I know some of you are from Cone College, so this will be a rehash. We wrote those challenges for the ASU Hacking Club so that people could get an intro to assembly without actually knowing assembly. So if all you know how to write in is like pseudocode, so essentially just math, if all you know is math, then you should be able to do the modules and learn how to do x86 programming up to the most basic stuff. We haven't added syscalls yet though, so that is a to-come feature.
Cool. How's the right, video look in the stream?
Let's see.
The stream looks good.
In Discord? Yeah, sorry, good. In Discord it also looks good?
Yeah, okay. Discord looks good.
Dope. Sweet. All right. Let us rock and roll. Okay, cool. So we left off talking about x86-64 instructions. This is what we're going to be going to. If you recall, at the very end, we were writing system calls in order to exit the program. And what I want to start with is... Where do I want to start with? Cool. I'll start here. So I like starting off with like hands-on challenge. So here is x86-64 code. So the challenge is already up on the CTF website. That is here. So understanding ASM. So what this question is asking you is, what's the value of the RAX register at the end of this code in hex? So this is something that I don't think we've talked about yet. I kind of have been assuming it a little bit, that you can go from what normal decimal base 10 numbers that you're used to thinking about and going and thinking about in hexadecimal. So this is where each digit has 16 characters. Putting that in with what we learned, basically the nice thing is each digit then represents 0 to 16 bits. And so you can, it's kind of a standard way of representing numbers on a computing system, because as we talked about, the CPU, right, these values in registers, it doesn't know what you, the programmer, intended for this value to be. All it is actually operating on is bits. So make sure when you submit the flag to prefix it with 0x. That's kind of the standard way to demonstrate that, hey, this next parameter or this next number that I'm showing you is in hex. And for those of you who know how to take this and compile this, I would rather you kind of look through this and try to do it all statically, so that way you can practice actually computing this. So what you should do, step through these operands. You can draw the registers or do kind of whatever you need to do to get this happening on your side. Interesting point, I think, is yeah. So if you don't know an instruction, if there's an instruction here that we haven't necessarily talked about, go look it up. Like, this is the point. And in these meetings, we're kind of learning how to learn. So I kind of set you on a path, give you a challenge, and then from here, it's up to you to actually go out, find the information that you don't know about these different instructions, figure out what the semantics are, and then we can go from there. So with that, I'm going to make this big, and let's give it like 20 minutes to see how that goes. Hey Siri, set a timer for 20 minutes.
20 minutes, starting now.
Thank you. So nice. And of course, I will then have to Man, OBS is exactly written by programmers. I'll put the code back up in a second. I'm figuring out how to do this.
Are you saying it's written by programmers because of all the options you have, all the levers?
Yeah, it's terrible. So like this windowed projector, you have to right click to get a screen that's just that thing, and this option to show in multi-view. But with the view, you'd think there'd be a view maybe here, or that would show you your screens in here. So this is where you can get a multi-view thing. So it's like classic kind of like open source developers. If you ever used anything like GIMP or something like that, that's supposed to replicate like a good professional tool. It can be really annoying because they don't. Oftentimes, open source developers do not take user friendliness into account. And if I wanted to do this,
I feel attacked.
Yeah. If the shoe fits, you know. Window capture. There we go. Dope. Dope. Oh God. This is insanity. You do have something about, that's cool. Dope. All right, that goes up there. And let me change. So now I have to set up a windowed projector for this. You'll get the flag later. Don't worry about that now. Oh, actually, yeah, if you're watching this video online, you should just pause it here. Okay, how about this? You can go to the stream. All right. Look at this. I'm even figuring out different change windows. So if you go on the Twitch, you can see that full flag. This is the meeting flag for today. And you should be able to see in Discord the challenge. I want to see everyone getting that flag. Zero solves, huh?
Should our answer have the 0x in front of it?
Yep. This is an important note about CTFs. So usually you want to double check and always read the instructions again, because usually it will answer that, or somebody else has had that question if it's not answered there. Ooh, one solve. Good job, Cactus Climber, first blood.
Man, that's the guy who stole the money from the ASU Hacking Club 2 years in a row.
What?
He won the first the challenge, the first meeting challenge. That gets you $20.
Nice. So you don't need computers if you have your mind. Your mind is the best computer. Ooh, that's the timer. All right. How are people doing? Let's look at the solves. 5 solves, not bad. right, let me... Boop. Okay. Let's what I'm going to do is I'm going to walk through like 2 of these. Let's say 3 of them, and that way then we can kind of go through them together, and then I'll give you another 10 minutes to see if that gets you unstuck. So I'll just kind of walk through how I would go about doing this. So right now I'm just going to add, so we'll keep track of what's in the RAX register at this time. So we're moving a constant value into the EAX register. If we remember from the previous slides, the EAX register is the lower 32 bits of the RAX register. What happens when we move a value into just EAX of RAX? What happens to the upper 32 bits? Yeah.
They stay whatever they were.
No, incorrect.
They get set to 0.
They get set to
Or they
0,
get cleared
exactly. Yeah. So there's a special feature that we got to keep in mind when we're reading these to just remember, oh, it gets zeroed out, right? So all of the top of the RAX register, so we know the first 32 bits are all 0. 1, 2, 1, 2, 3, 4. And then the next, because this is a move, everything becomes exactly the same. So it's 4, 1, 6, 2, 4, 2, 6, 4, 2, 4, 6. It looks like, yeah, 4, 2, 4, 6. Cool. And now a load effective address. So LEA is load effective address. And we're going to put, so, and this, let's, ooh, nice beach ball. So RAX has this value. So do I know what is inside the register RSP?
No.
Do I know? Yeah, so I don't know anything about RSP, right? And load effective address, remember when we have a move, when we have brackets around the source of the move, usually that means a memory dereference, which we'll get into more later. But the interesting thing here with load effective address, it's calculating what address would it fetch. So oftentimes you can see like RSP plus 0xa, so that'd be plus 10 bytes, whatever's in RSP plus 10 bytes. And the load effective address means what I'm doing is copying that into RSI. So it's actually just a fancy, like the way it is a fancy copy. So, but like what we're tracking here, what we know statically is we have no idea what's going to be inside this RSP register. Do we know anything about what's going to be inside the RSI register after this instruction executes?
The value RSP was pointing to?
Yeah, whatever, exactly. So whatever was in RSP. So I actually don't, like, it's essentially a copy. So it's saying after this instruction executes, whatever inside the RSI register is exactly what's in RSP. Okay, sweet. Let's do this last one. Just together, and then I'll let you finish out the rest. So this last one is moving into AL. Which register is associated with AL?
The lower 2 bytes of RAX.
Almost, very close. It's the lowest byte. So it's not the lowest 2 bytes.
Right.
Yeah. Okay, yeah. So it's the lowest byte of perfect. So in our diagram, right, it would be it'd be this byte here. So now this, again, this is where the difference is moving something into AL or EX or EAX or AX, I guess. Sorry, not EX. doesn't change any of the other bits. It's only this special case of when we're moving a value into EAX that it zeroes out anything that's higher than that. So all that's going to change here is, and now after this we know RAX is going to be equal to this value, and we replace the last byte with AB. Does it matter if we do uppercase or lowercase AB? I stumped him.
I honestly don't know if it matters.
It's a trick question. It does not matter.
Yeah.
Yeah, it's a in hex, uppercase and lowercase letters doesn't mean anything. Just like there's no concept between uppercase and lowercase 2 and 4, right? We're using the values A through F to represent numbers. A represents 10 and F represents basically 15 for the value for that digit. So it doesn't matter if it's uppercase or lowercase. I guess actually depends on context, I think, of if I do uppercase and lowercase. It's actually interesting to think about. I never thought that. Cool. So let's give people some more time.
I have a question about that first.
Yep.
The move to EAX. So is that universal for all of those E registers? So like EBX and ECX, they all will zero out the top 32 bits?
Yep.
Okay.
Yeah, so they're special when you move a constant value. I think a constant value or another register, I believe. I have to double check that one though. Zion, do you know?
What was the question again?
If you move like EBX into EAX, does it also zero out the top 32 bits?
Of EBX?
Of the destination, obviously not the source.
Yeah, it should zero the top.
Yeah, I think it would. Yeah, that's what makes sense because I've actually seen this behavior happen.
I thought I had like some kind of type, this is the wrong term, but a type mismatch when I've tried to do something like that. Like it would say that the size of the one register didn't match the size of the other register.
You mean like if you're doing something like move EAX, like something like this, move EBX into EAX?
Oh no, EBX. No, sorry. I thought you were saying move like RAX. So move EBX into RAX.
Interesting.
I've had them say like the size. It complained something about size, but maybe that was specific to something I was doing at the time.
I can't remember if it fails or not, but the problem is it may not know how to do this, right? Because you have and we'll get into it. We didn't get into assignedness and how you actually represent integers and all that fun stuff, but it may not know. Essentially, it doesn't know what you want to do with the uppermost bit, is I think the key problem here.
Oh, okay. And maybe that's what it was complaining about the entire time, but I just wasn't understanding the error.
Yeah, it could be. I'd have to look at the exact case. Yeah, oftentimes that's why when we look at like the decompiled output, move instructions are supposed to have a size associated with them of how much data you're moving. But in all of these cases here, the compiler can figure out. So it knows we're moving 1 byte here into AL. Here it knows we're moving a double or double word, so 4 bytes into EAX. So it automatically figures it out and then figures out the right x86 instructions there. Cool. Any other questions before we break for time or break for finishing this out? Cool. All right, we'll put 10 minutes on the clock and we will meet back here. got to 6. Good job. right, that's the timer. Let's check where people are. Eight solves? Okay, I will let the people decide. If you're still working on this and want more time, say something. Rawr. Yeah, we can do 10 more minutes. I think that's good. All right. And if you're already done, go read about x86 instructions. Lots of craziness there. Yeah, malware is the big one. Actually, that's a great question. What would be the thing I was looking for is looking to see if Linux has, because there's actually a lot of handwritten assembly in Linux. So I wonder, I don't think there's an index for Linux where you can look at like every occurrence of a certain instruction in like the handwritten assembly in Linux. Yeah, but I want a better grep, man. Grep is lame. Like, I want to see that for all the instructions, not just that single instruction, right? I would want to see what other ones they have. Or what's the one they only have, like, one of?
So basically like a radix sort of like all the handwritten instructions.
Yep. That'd be super
That'd be
cool.
pretty cool. We can host it on Noob College.
There you go.
Nice.
wondering if there's some crypto algorithms that would use that instruction or something like it. I don't know. Yeah, I think so. I think crypto may be a decent example. Nine solves, great. All right, that was the 10 minutes. We just hit 6 o'clock. We got 9 people, 10 people solving it. Awesome. All right, we'll move on from here, but this will stay up. The challenge will stay up. I think it's important to do these kinds of challenges and thinking about the problems in this way because it really helps you understand what's going on, right? So it's kind of a broader philosophy about programming in general. So I really do believe that like you get better as a programmer by actually doing and actually doing the thing that you're supposed to be doing. So, or sorry, both reading code and writing code. If you spend all your time writing code and you never learn how to read other people's code, you're actually going to have a really difficult time when you go into industry because nobody will. You actually spend most of your time reading code, not writing code. Similarly, if you just spend all your time reading code, you will be very poor at writing code. So you want to make sure you have a good mix of both. So with that said, let's change windows. There we go. Full screen and full steam ahead. And what I need to do is get like a board where I can switch between these scenes. That would be pretty cool. Okay. Great. So great job to everyone who's solved it so far. Very awesome. And let's continue. Where did... Cool. So let's continue our exploration of x86-64. And so kind of the interesting thing that you can see even from here, right, is this is 5 lines of assembly code. There's one weird instruction, this ROR instruction. It's kind of the one you probably won't see very often. So that's why I specifically included that in here so you would be able to go and look that up and understand kind of what that does. Yeah, cool. So we talked about system calls already. Last week we were able to write a program that was able to call, make a system call to call into the exit system call. And remember, exit was very simple. Let me open up that code here. Oh man, this is cool. So this code was very simple. So we were calling exit 5. So, and actually we adjusted this. It should be RAX RDI. So how did we know to move 60 into RAX? What does that 60 mean?
Isn't that the system call number in the table listing? System table listing?
Exactly.
Yeah.
So we go to our handy dandy system call table. We look for sys_exit. And we see at 60 is 6exit, and the first parameter there is the error code. So that's how we knew to move 60 into RAX. And again, it's not hex, and we know it's not hex because it doesn't have the 0x in front. If it was 0x, it would be, and I would need the other thing, this is why you shouldn't be too scared of hex, just because honestly, like, don't think that people do this insanity where they translate between them. Some things I can do, but something like, what's 60? I have no idea. It's going to be 60, or 6, what would it be? 6 times 16 times 10. But we can I just use a calculator, which makes me not have to think about it. So I can do 60, turn it into hex. So 60 in decimal represented as hex is 3C. and I can do 60 in hex would be 1096. So if I go down to 96, that would be the syscall get time of day, which is very different than what we wanted to do in this example of exit. Okay, great. So we got 60 from here. We got that from the table. Why are we moving 5 into RDI? Yes, that's the exit code argument. So this is again the this is the calling convention basically that this is the ABI. ABI stands for is it application binary interface? I actually can't remember what the A stands for. But this is the somebody. I don't think it stands for abstract, but somebody tell me what that is. But that is the contract between the user space program talking to the kernel. So this is the way to tell the kernel, hey, I'm going to call this exit system call. And it's A for application because that's the application's binary interface to the kernel. So that it says, hey, when I call the system call exit, I will put the first argument into the register RDI. And that way the kernel will get into very eventually maybe how that happens. But then the kernel is able to see that, read the register, and say, oh, they're trying to access the RDI register. They are wanting to exit, and they're giving me the exit code of 5. So I'll do whatever I need to do in my operating system to make that happen and then kill the process. So super cool stuff. Okay. Now, let's do cool. Okay, so let's do what's the first classic program that you write in every programming language?
Hello world.
Yeah, hello world. Something that prints out hello world. We haven't even done that. All we've done is I guess you could call this goodbye cruel world. Right, we're just calling exit with some value. So let's do a hello world. So let's go through this. I'm gonna call it hello underscore world meeting, because obviously I've already written this. I'm gonna copy the code from the start here that I know I need. Okay. And I'll say the purpose of this call. Now, I have syscalls here. The use of this table is to tell you the exact arguments and where they go in for each system call. It's kind of a pain to figure out what system calls do. So let's do. There we go. Okay. Sweet. Okay, so let's. Oh, yeah, we want to do man, and remember all the system calls are in the second section of the manual. So if I do man to write, it tells me what am I going to do? Write to a file descriptor. So we're going to get into what that is in a second. But basically, we call write. We have 3 arguments, the file descriptor to set, a buffer, so a pointer. This means a void star, so the star means a pointer. So I want some value that points to a buffer of what the contents are that I want to output. And then I have some count of how many bytes I want to put out. So, and then we can look at the semantics. So write writes up to count bytes from the buffer starting at buff to the file referred to by the file descriptor FD. The number of bytes written may be less than count if, for example, there's insufficient space. Okay, so we may not actually write all of the bytes that we think we're going to write, or the call was interrupted by some signal handler. For a seekable file, so a file that we can actually seek to different places and move to different places, writing takes place at the file offset, and the file offset is incremented by the number of bytes actually written. This makes sense. So wherever we are in the file, we're going to write some bytes, and then if we write after that, it will occur after that. Cool. All kinds of other options, blah, 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 blah. Huh. POSIX requires that a read that can be proved to occur after a write has returned will return the new data. I didn't know that. Interesting. Learn something new every day. Okay. And the return value, on success, the number of bytes written is returned. 0 indicates nothing was written. It is not an error if this number is smaller than the number of bytes requested, blah, 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 blah. On error, -1 is returned. Okay, we can stop reading there. That has everything we need. So we want to, now, we don't know yet what to put in this FD or this buff. Count seems pretty straightforward, the number of bytes we want to output. So let's try that. So we want to call write to some file descriptor. We'll use 1 for now, and we'll look into why exactly that is in a second. But we want to write to, let's say, file descriptor 1. And we want to write out the string hello world. Maybe a new line because we're good people. And then how many bytes do we want to write out? Do we just do 1? If we did 1, what would happen?
We'd get H.
Yeah, we just print out H and nothing else, right? We actually want to print out the whole dang thing. So we want to make sure to do, let's see, how many characters is there? We are lazy. We'll just count 1, 2, 3, 4, 11. 11, or is it 12? This slash
It's
n.
12 with the new line.
Yeah, so it's, what was that, 12 you said with the new line, or?
Yeah, with the new line.
Okay.
Or is it 13?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13 with the new line. So the slash n is a way of basically escaping and showing that, hey, I want to, I want a new line character, just like we talked about escaping in the context of shell arguments. So here I don't want a, I want a literal new line. So that's how I'm representing that right now. So it should print out hello world, exclamation point, and then one more line afterwards. Cool. Okay, we know eventually I want to call syscall to write out hello. We also, let's not be monsters. Let's call, we want to call exit. And the standard, remember when we talked about return codes of programs? What was a non-error return code? How do we indicate that everything was fine? Yeah, 0, a return code of 0. And that actually, if we remember, reading the man page for write also will return 0. Shoot, that's incorrect. Write will return -1 if there was a problem. All right, my point did not stand. I guess the point is you should read the documentation and do what it says. So here we move 0 into RDI. So this will call exit 0. Say, hey, everything went well. Okay, we want to call this write system call. We can break this up. First thing, I called this move. That's gonna not like that. So what am I moving into RAX? How do I figure out what value goes into RAX? You don't have to tell me the value, but how do I figure out what value goes into RAX? Somebody said 1. How do you know 1? Yeah, we look at the table. We go back to our handy dandy table and we say sys right, RAX is 1. Great, set that. And then I can even, let's move that here so we can reference it while we do this. So now in RDI, I need to put my second parameter, my file descriptor. So I can put 1 here because the file descriptor I want is 1. We'll talk about the buffer in a second of what we want to write out. But after we do that, so I'll write a little, excuse me. I'll write a little note to myself here to do set up RSI with buff. So now I can move in here into RDX 13. Why do I want 13 into RDX?
That's our size.
That's our size. And we know from this table, the count is the size, and that goes into RDX. Beautiful. Okay, now how do we do this? So the first thing to think about is we need the bytes of hello world somewhere. We can actually, if you do man ASCII, this shows you the ASCII table. So if you think about it, it's actually 100% arbitrary of like, how does the computer represent a capital H or a capital A? Is it the value 0? Is B 1 and C 2? What about uppercase and lowercase? All that insanity. So we need some way, again, remember, because the computer itself knows nothing about the CPU, the registers. It only cares about the bits in there. It doesn't know that they actually represent things. It only represents things to us. And so we use ASCII, which apparently is the American Standard Code for Information Interchange. I guess that's a pretty nice name, except for the American part, but it's American because it encodes basically English really well. So it's actually a 7-bit code. It's kind of silly and kind of ridiculous. So we can represent different letters. And so these are the characters. So how to read this is there's 3 different ways of representing the character here: octal, decimal, hex, and then the character itself. And there's a double column table here. So you can read this as 0. So the byte 0 is the character null, and it's the null character. Not very interesting. The @ sign is hex 40 and decimal 64. Capital A actually starts at hex 41 and decimal 65. Character B represents hex 42, decimal 62, and we can actually go down this table for everything. So every character that we care about and can represent here. Now, if you think forward to, well, how do you display insane ASCII art? Or, you could ask a very reasonable question like, hey, I don't speak this English language. How can this help me represent my language? And the short answer is it can't, because this was created in, I don't know, the 70s or something. And before that, when they were trying to get things to work and weren't really thinking about that literally everyone on the planet would use computers that wanted to talk to each other. So they had to extend ASCII into like Unicode and all this other madness, where now every character is not just 7 bits, but we actually use 8 bits. So each character is essentially a byte. It's not that each character is a byte anymore. It's all complicated. And to be very honest, I don't understand how it all works, but I know that it is interesting. Okay, cool. So we need those values somewhere in, so we can look at this table and we can say, where's the character H? The character H has decimal value 48. So we actually need somewhere in memory these bytes. Now, just like how we use this .text directive to tell the assembler, hey, I have some text that the text in this case is code. Hey, this stuff's going to be code. What I really want is somewhere to put my data, so a .data section. And then I'm going to want, so let's experiment. So we can actually use something we haven't talked about yet, but just like we had with this main. So main is actually just a label that represents some point in the program that's actually starts right here at whatever is after there. So I'm going to create another label called HW for hello world. And actually, let's spell it out. Now I'm going to do something that I didn't prep for. Assembly. I want to put raw bytes. Does anybody know how I put bytes in here? Is it just like, let's see which ones I want. 48, H. Well, all right, I'm gonna cheat for a second. Yeah, I know I can do dot string. All right, I'm gonna cheat. So obviously working with ASCII values is something that you will be doing a lot. So the assembler has ways to support that. So what this says, this dot string tells the assembler, hey, at this point in creating this binary, I want you to put the values into memory, the literal values that represent HELLO space WRLD exclamation point and then new line. I want you to put those values in memory, and I want you to call that memory location hello world. Which means we can do something really nice, just like we talked about before. We can use load effective address to move. So this is basically now, so hello world is not a register. It's not a constant. It's a label that the assembler goes. So essentially the assembler goes, okay, this dot string, I'm going to put at memory address 1000, whatever. And so what we're doing here is, hey, whenever you see hello world, replace it with 1000. So what this does is would move the value 1000 into RSI. And this means that RSI now contains a place in the memory, the value inside RSI, the memory at that location. The first character should be an H. The second character should be a lowercase e. And let's actually look at that. So I think this looks good. Let's save this. And then let's go over to this fun guy. Okay, of course, Dropbox is not updating fast enough because yeah, because my computer, I think you can see it's using like all of my CPUs to stream all this video to you and the nice people at home. So I will do something really lame and use cat to transfer my file over. So I'm going to hello. And of course I had to call it something really large. There we go. Paste it. Now I can use Control D to tell cat that, hey, there's no more input. You're at the end of the quote, quote file. So it knows to stop doing that. And now I should have my file there. Very handy. And there we go. I have hello world meeting, and I can do GCC dash. Now there's one thing I need here. It is, there we go, PIC. relocation against data comp used. Yeah, okay. There we go. No pi. No pi for you. So what it's complaining about is it's basically saying, hey, you're using this fixed memory location of this hello world. And the problem is by default, GCC compiles and makes it so that the code and data of your program can be put, or the code of your program can be put anywhere in memory, not at a fixed location. And so it's saying, hey, I don't know how to do that for this. So what we can do is compile that and say, hey, don't do that. Don't use that. Put things at a fixed location. Interesting thing, I can run the program strings. I don't know if we talked about that before on there. Strings is, of course, I ran it on the code itself. What I want to do is run strings on a.out. And it'll show me a bunch of stuff, but it will also show me my hello world string. So this is actually a really good tip for CTFs. Strings is one of the first thing that you want to do. What it does is literally looks for, I think at minimum, printable character sequences that are at least 4 characters long. And you can actually use an option to give more characters. So this kind of shows you in a program what kind of strings there are in the program, which can help you know what it's about. All right. Yes, we'll get to that in the chat. But first, let's run it to see if it's correct. Boom, we got the hello world. Okay. First thing we want to do is run strace on it. So remember, strace is the thing that shows us all the system calls that are happening. So this is every system call that our program is running. And again, like before, we get a lot of kind of the garbage and gibberish where it's the BRK is to set up like a heap environment. The accessing this ld.so, it's looking for different files for the loader to load the libraries that we may or may not need. It does all that, M protects things, blah, 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 blah. But the super important thing that we care about is this write. So it writes out to file descriptor 1, the string hello world, and it passes in 13. So it printed out 13 there. Excellent. Now we're going to do something I hadn't planned on doing yet, but since it was asked, let's look in the debugger to see what's going on. So GDB allows us to poke around, and the problem is your version will not look like mine at all. Just kind of roll with me for now. We'll get to like setting our stuff up into Jeff and all that fanciness. For now, we should be able to get by just by using things like strace and the compiler. If the compiler complains at you, you'll have problems. Especially when just at this point where we're just writing assembly to call syscalls, you can use strace to basically completely understand what's going on and what's in each of the registers. But I'm going to set a breakpoint on main. I'm going to run this program. And we can actually see, so this very cool output until Zion becomes the Jeff master and replaces this with disassembly. We can actually see, look, this is crazy. We see all of our code here, right? We see move 1 into RAX, move 1 into RDI, load effective address, whatever the hell this thing is, into RSI. That's very not helpful. And of course I just quit, okay. Cool. So yeah, we moved this thing 401, 601, 026. Is this the ASCII representation of HELLO? Yeah, it is definitely not. And we can actually look that up, right? We could open up a new terminal window. Man, ASCII. right? And we actually already looked up, and we know this is hex again because of the 0x, which is cool. And of course, the funny thing is my ASCII table is different than the one we just looked at because this is on a Mac. But if I look for capital H, I should be able to see in hexadecimal that H represents 48, and we don't see any 48 in here. So it's definitely not that. Okay, cool. So it's not there. Let's look. So what is in here? So let's step through this. So one of the cool things with GDB, we can print out values. So we can do p/x to print out, and then the /x means in hex. Print out whatever is in RAX. And so right now there's just some crazy value in there because again, I haven't actually executed any of my main code. So I do SI to single step an instruction. And now we can see that this shows me, hey, I just finished executing this instruction and I'm just about to execute this next instruction. So if we look and print out the value in RAX, now RAX changes 1. This is great. This is exactly what we want to have happen. Let's step again. So now we can p/x $RDI. Now RDI has the value 1. And now something's going to happen to RSI. We can actually look, let's look at RSI, check the value. It has this 7FFFDE38. Okay, step instruction. Print that out again. It has now the value 601028. So what the heck is going on? So just like that was mentioned in chat, right? If we go back to our assembly code, the string hello world is 13 bytes. What's the size of the RSI register? How many bytes? 8 bytes. Yes, thank you. So what's going on here? The difference is we're not actually putting the string HELLO space WO and then asking it to print, because we'd only be able to print 8 characters at a time because that's only what fits in a register. So we need to actually pass a pointer to memory. So what's in RSI? So we'll do what's in RSI right now should be the location in memory of the bytes HELLO space WORLD exclamation point and new line. So I can look at this. I can do now I'm doing something very different here, and I'll explain it in a second. I think it's BX would work, but let's see. $RSI. So now what I'm saying, instead of doing a P, so P means print out what is inside that register, right? Show me the bits of the RSI register and interpret them as hex, and this is what they are. What the X is saying is examine instead of print. So examine what is at the memory location 601028. Show me those bytes in memory, and everything after the slash is telling it how to print it. So the X means print it out in hex. B should mean interpret everything as a byte, so only show me each byte. And 13 tells me how many to print, so 13. So if I hit enter, this should be, was 48H? I should have kept up that table.
Yes.
Yeah? Awesome. Dope. All right. So H was 48 and 65 should be lower. It should be E. So we look here. We see, wait a minute. E is 45. What's going on? That's 65. Why'd that happen?
Lowercase.
Lowercase e. Yeah, thank you. 6C should be L, and we can actually see there's 2 of them. So LL, that would make sense. HELLO. Hello. 20. 20 is weird. We haven't talked about that. 20 is actually a space, so it's the space character. Great. 20 space 57 should be capital W, and yes, it is capital W. Hello. W, O, we actually already did O. WORLD21 back to our table is boom. This is an exclamation point. This is amazing. And 0A, that's interesting. So 0A is here. And NL here stands for new line. So this is why we get the new line at the end here. So again, this is actually really cool because now we're not limited by the size of our registers and how many values we would have to print. Think about if we only had that. We would have to continuously call the right system call with at most 8 characters in some register. And so that would just be a massive pain in the butt. But what we can do is tell, hey, this is where the bytes are located in memory, and start printing them out. And how many do we print out? Well, it's the next line. So it is move D into RDX. And this time I will P/D, I think, which will do it in decimal, RDX. And it should tell me 13. So it's going to print out 13 of those characters. I do that system call. Boom. If I scroll up, we can see this beautiful, beautiful hello world here. So it printed out our string based on that syscall. It's then going to move 3C into RAX. It's then going to move 0 into RDI. And then, boop, everything quit just like we hoped. Okay, very, very cool. Let's make that change to see what would happen if we... What the heck? Oh, cool, Vim. All you Vim people can... So let's do this. Let's change this to a move. So basically, what if we moved hello world into there, and we'll see what kind of error message it gives us. I think this is, does anyone get error messages when they compile their programs or anything?
Never.
Never? Just all a bunch of
Just kidding.
great expert level programmers. Yeah, everyone gets mistakes and errors, right? So it's definitely something to not freak out about, right? Everyone makes mistakes. We miscompile things. We forget a semicolon. And so actually one of the fun things to do if you have a working program is to actually introduce things that you know should fail and then see what the compiler says. So here we just changed that load effective address to a move, and we compiled it and went, oh shit, the compiler didn't say anything. The compiler just compiled that. So let's kind of look and see what's going on here. So let's run it with /a.out. Okay, it didn't print out anything. That's interesting. Let's strace it. Ah, cool. Okay. Yeah, so we can actually see, look at this, what it's printing out here, right? This is the value that's inside the RSI register, right? And it has the bytes that we just talked about, 48, 65, 6C, 6C, 6F, 20, 57, 65. Those are the first 8 bytes of our hello world string. But the return value here, rather than returning what it should on a success, which is the number of bytes written, it actually outputs a -1 and says, yeah, I'm sorry, there's actually this is a bad address. What you gave me is an address that does not exist. So this is a cool error that we can see, basically see here. That if we tried to pass that in, and actually over time you get good for eyeballing what's an address, and we can see that this is actually just way too large to be an actual usable address, but that's kind of more advanced stuff. Okay, cool. Let's change it back. All right. Hello world. Beautiful. Man, gotta love that hello world. All right. So we were able to call hello world, but let's dive into this file descriptor thing, right? So we were able to, we told it to write to 1, but what the heck does 1 and what does 1 mean? Right? So how do we actually understand this function signature to say, okay, this write takes the write system call takes in a file descriptor, a void pointer, so a pointer to a buffer, and the count. Okay. So file descriptors. So the first thing we have to look back on is what the heck is a file descriptor? So programs, as we know, want to be able to read input from a user and show them output. And so file descriptors are really nothing fancy. They're literally just an integer, as we already saw. We are familiar with the file descriptor 1, which for some magic reason, when we wrote to it, showed up on our terminal. And basically the program uses that to tell the operating system, hey, I'm interested in this file, and this is the specific file that I'm talking about. So the reason is if we look at the open system call, so let's look at that in the man pages, man to open. So we run this, and we can see that it takes in a path name, some flags, and the open system call opens the file specified by file name. If the specified file does not exist, it may optionally be created, blah, blah, blah. The return value of open is a file descriptor, a small non-negative integer that is used in subsequent system calls like read. How come read says read to here and not read in the whole like function signature, or like write, which we looked at? Write doesn't have 2 parameters, it has 3. What's this 2 here?
Looks like the page or section in the manual.
Yep, exactly. So we know, oh, if I want to learn more about this, I need to do man to write, or man to read, or man to lsteek, or whatever. Yeah, perfect. Thank you. Okay, so the return value, blah, 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 to refer to the open file. The file descriptor returned by a successful call will be the lowest numbered file descriptor, blah, blah, blah. Nobody cares about that. But this is very cool. So this means that when we call open on a file, it returns us an integer that if we pass to read and write and lseek and whatever, it will operate on that specific file, right? So it's really cool. This means that the operating system is doing work for us. It's basically, the operating system is doing all the work of deciding and keeping track of, oh, this file on the actual like physical hard drive maps to this open file descriptor in this program. Now, but that still doesn't help us. Where the heck did 0, 1, and 2, and 3 come from? And actually, let's go back to our program and let's, so we strace. So we actually do see an open, a family of open. So this open at is basically, you can look it up, but it's equivalent to open, and that returns a file descriptor. So it's cool. We can actually start reading and understanding this. It's calling open at, passing some flags, a couple flags. It's saying /etc load so cache, and it was able to find it, so it returned a file descriptor 3, which it then uses as the argument to fstat. If we looked at fstat, I would bet dollars to donuts that this first parameter here is a file descriptor. And then close is another one we didn't talk about that returns a file descriptor, or that takes a file descriptor and closes the file and says we're done with it. And that's why after we closed it here, we open another file and it returns the same file descriptor 0. So this is, the same file descriptor 3. So stuff happens here. We read from it. Now we're reading from that file. We fstat it. We do other stuff, blah, 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 blah. And then we finally close it because we're done with that file. But in this whole thing, at no point in here do we ever call open and get a file descriptor of 0, 1, or 2. So the first thing that was returned was 3. So what is going on? Well, Turns out they're just special. So this is one of those things that I can't tell you there's a great reason for it. I think the reason is that, as you'll see from what these values actually are, it's very common for a program to want to either read or write from them. So they're basically by default open. So every process has the following system file descriptors open by default. And I highly encourage you, literally burn these into your brain, what they are and what they mean. This comes up so often that it really, you can't help but learning it, but actually learning it now will save you time. So the first is file descriptor 0, which is standard input. And this is reading input from the user. So this is how you get and are reading input from the user. And it's also, usually we abbreviate it to standard in, std in. Anybody do Java programming? Nobody's done any Java programming? Yeah, in CSE 110. Yeah, so actually, let's save that for a second one. I'll come back to there because my Java's super rusty. But okay, then file descriptor 1 is standard output, and that is the output that goes to the user. So this is why when we when we wrote to file descriptor 1 and called that system call write, that output went to the user, to our terminal, literally our terminal. And that's called standard out, std out. And you'd think that's all you'd need, right? You'd think you just need input and output, but sometimes crap happens. And so you have error cases, and we'll see why in a bit that it can actually be useful to separate out, where a program's output goes versus where the error messages go. You could think if you want logging or alerts whenever there's an error, so that's called the Scd error. So when you are using Java and you want to print out on the terminal, what's the Java command for that? Is it like system.out.println? Yeah, system.out.println. So the really crazy thing is this does all of this under the hood. So when you're running Java on a Mac, it will eventually translate that to a write. So you can think of Java itself, even though it is not, you're not doing assembly, you're coding in this other higher level language Java, but system.out means standard out. That's what that out means. Is it system.in is the other one? I can't remember how you read input in Java. It's been a very long time. I think you build some scanner and you blah, 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 but I wonder if that's in system.in. Yeah, it is in system.in, and that specifies standard input. So you can see those concepts are already existing in languages that you're already familiar with. So you're technically not learning anything new. What you're learning is how the stuff actually works, which I think is fun. And hopefully you do too, and hopefully that's why you're here. Okay. So now that we know this, what if we write a little simple program, a little echo program? So a program that takes our input and prints it out, just like cat. So we need something that takes in input and prints it out. But where do we put the data? That's where we need to go back to the other slide to learn more about assembly. And we should see something nice. Remember we talked about the architecture. So we have different places of creating memory. So like we saw, we can tell the compiler, hey, using .data, we can say, hey, I want this data at this location. So it'll always be in this fixed location. I know exactly where that data is. But what we can do is we can use what's called the stack. So this is when we talked about and we looked at RSP. So RSP will contain an address that is the current location of the stack. And by subtracting from it, we can actually get values. We can claim values on the stack. And this gives us like memory that we can use very easily. So I will show you how to do this. So let's do, we'll call it echo because I don't want to call it cat. Okay. And let's call it echo meeting dot capital S. Okay. Yeah, I know it. I want a new file. Okay. And we don't need any data section. We'll just do this. Yak these lines. Cool. Okay. Now, the first thing I want to do, so let's have this, let's say purpose of program, read in up to 100 bytes from standard in and output that to standard out. So the way the stack works at a high level that we can think of now is what I can do is if I subtract values from RSP, that essentially means I'm claiming them as my own for this stack. So by subtracting 100 from RSP, I can, and let's also steal the ending code here. So I always want to exit cleanly. Cool, exit 0. So I subtract 100 bytes from RSP. This will adjust the stack pointer down so that now I have a guaranteed 100 bytes that nobody else is using. And then what I will want to do is call read from, what was standard input? What file descriptor number? Did you forget already? Dun, dun, dun. Standard input is not 1. Remember we wrote to 1 for hello world. You now have a 50-50 shot now that I said that. Yeah, 0. So I want to read from 0 into RSP up to 100 bytes. And then I want to write to now standard output RSP 100 bytes. And it is in this place where I leave you. So what I want everyone to do from now until next week, write the rest of this echo function. Write the read and the write. So just like how we did this with the hello world function, you can use that in order to figure out how to do everything, set up the registers correctly, call the system call for read, and then call the system call for write. And so you should be able to, when you're done, so I do have a finished version here that I won't show you what it is, but I will show you how it looks, echo.s. And when you have that, I should be able to input something and it echoes it back out to me. Cool. Fun homework. Writing code. And then what we'll do here is we'll start off with finishing this code up together collaboratively. So bring your own ideas and then compare what you did with what we did. If you get stuck at some place, please let us know so we can talk about that stuff. And then we'll go from here, and then we'll extend this program if you want to get advanced already to continue to just keep reading until there's nothing more. So we'll go over loops, and then we'll keep going from there. And I will... Okay, let me stop streaming so stuff doesn't go crazy. You have anything to say at the closing, Zion?
Nope, I don't got anything.
All right.
just play the CTF this weekend.
CTF,
Starts on
CTF, CTF,
Saturday.
CTF.
CTF, CTF.